Thank you. See what I mean? Okay. I do that when I like check my email.
Yeah, no, I think there's some response.
You never know when somebody's gonna like zing you with like a private email. Okay, so I think we did this first one together. With looking at the graphs, the easiest thing to do is to look at the slopes and infer what the next thing should be from that. So when we're looking at a position versus time graph, the slope of that graph tells us about velocity. So with this first one, we can see that the first half of this is a constant positive slope. So that tells us we have a constant positive velocity. So this should be a straight line in the positive portion of the graph. Then after that, we've got a constant negative slope, and this is steeper than the initial one. So it's telling us that this velocity for the second part is going to be a bigger negative velocity than the initial one. So if this is, whatever this height is, I want to make sure that I go further than that down at the bottom for my second velocity. Then for acceleration versus time, I just need to look at my slopes of my velocity versus time graph. Both of them have constant velocities, and neither of them are zero. So it's higher, but there's no change. So when I see a velocity versus time graph where there's regions with no change, that's telling me I have no acceleration, because acceleration is a change in velocity. So this should be straight across the bottom. Sorry, by straight across the bottom, I mean right on the zero line. Then there's our motion map down here. When you draw a motion map, your motion map for velocity should be the same positions as your motion map for acceleration. So in this case, I'm going to start away from zero, move in the positive direction, then turn around, come back faster in the negative direction. So I'm going to start in a positive place, and I'm going to move away for a couple of seconds, and then I'm going to reach my peak and return, but I'm going to go faster. I'm going to kind of exaggerate it a little bit. All the way back down to zero. So this is where I started. And move this way and then come back. When I do my motion map down here, my dots need to be in the same place. So I'm just going to copy all my dots. I even do that before I draw arrows, just because arrows kind of clutter it up. And then my arrows are going to look like this. For my acceleration, if we think about what these represent, this is giving us a clue about the acceleration. And so there's an analogy here where these arrows are like looking at this space here. I have some positive ones and then negative ones that are longer. So these are in the positive direction and shorter compared to these. For my acceleration graph, my lines are going to be attached to the idea that we see in our acceleration versus time graph. You guys see how it's zero all the way across here? So none of these should have any points. Now, those of you who are in mathy things, yes, Ethan.
Why is it the acceleration still has points where it's like moving, like, and it's not just all like at the, say it starts at like 3 meters. Why aren't all the points at 3 meters? Like, why does it change when there's no change in acceleration?
So which part of this are we talking about your motion map?
Yeah.
So why is there no change in acceleration, like right here?
No, like why are the dots in different places when there is no change in acceleration?
They should be in the same place. So when we're saying something about velocity, the velocity is drawn as the arrow length. So where the dot is the position where it's located. So where it is telling us about this graph. Because the axis on this is meters. The arrows are the velocity. So the dots are the position. The arrows on the velocity motion map are telling us about the velocity. And then the arrows on the acceleration one will tell us about acceleration.
Okay, so there's just no lines.
For
acceleration.
Right. Yeah. So since there's zero acceleration here, there's going to be no lines, no arrows. This one's no arrows. Wow, because acceleration is 0 meters per second squared. Then for the description, there's lots of things that you can write here and be okay. What you want to do is talk about where your object starts and then any motion that it goes through. So this says that the object starts at a positive position, right? I'm just saying it doesn't start at 0. I don't know where it is, but it doesn't start at 0. And the next, sorry, that's my mom. No, sorry, it's my mom. Okay. It starts in the positive position, and then the object moves at a constant velocity in the positive direction. Then the object turns around and moves to 0 at a higher speed. We can say that's a higher speed and it's in the negative direction. Or you could just say at a greater negative velocity. Does that make sense? Did anybody say it a different way? All right. Anybody have questions about number 1? No. Okay, next one. So when I look at these, one of the things I look for is does it have a constant slope? The other thing I look for is there a place where the slope is 0? And so looking at this one, we can see that the slope is 0 at the very beginning, so our velocity at the very beginning must be 0. So we can just go ahead and draw that on our velocity versus time graph. And then if we take our slopometer, put it on our graph here, if we move it along the line, we can see that this thing has to rotate and it has an increasing slope. An increasing slope tells us that it has an increasing velocity. The velocity is getting greater. So our velocity versus time graph is going to look like this because it is a positive slope through all of that motion and it is increasing. For our acceleration versus time graph, what we're going to do is look at our slope of our velocity versus time graph. How does the velocity change with time? And this line is constant and positive. And so if we've got a constant and positive line for velocity versus time, then our acceleration is going to be constant and positive. So far, so good. Okay. Our motion map.
Dr. O'Malley, is Jack Palmer in the room or online?
Yes.
And how about Kimberly Washable?
Yes.
Thank you.
Thank you. So now we're going to draw our motion map. We're going to start with our object moving very little. The change in the displacement is very small compared to what happens at the end of the motion. So down here, we're going to start pretty close together. I'm not going to start at 0 because I'm not at 0. So I'm going to start close together and then spread out. I'm going to repeat my dots here for the acceleration motion map. Now, my arrows for this one should look kind of like what would happen underneath this. So my arrows, I would expect to get longer. I know that I should draw them with a distance that's halfway between the 2 points. So when I do that, I notice that my arrows do in fact get longer. So that's reassuring. For my acceleration motion map, I can expect my arrows to look like arrows if I stuck them underneath this line here. They're all the same length and they're all positive, so these should all be the same length and all positive. Now, if I wanted to be very meticulous about this and actually be quantitative and use numbers, what we'd be able to find is that if we took the velocity here, plus the acceleration here, we would get the new velocity because acceleration tells us how much increase you have in your velocity each second. So that should work out if we actually bother to do the numbers for that. Another way to think about it is what would you have to add to this arrow to get an arrow this long? And the answer would be the number that goes with this. This isn't necessarily to scale, right? I just drew qualitative lines here, just ones to show the trends. But if I was actually paying attention to the numbers, you'd actually be able to do that. So let's see, object. Starts in a positive position. I'm going to say moves.
Is it possible that we know that it's positive? Like, what if it was negative?
What if that was a negative position?
Yeah.
Then we'd have to change, we would have to assume that this was the negative end of the line and this was the positive end. And if that was true, then this wouldn't match. Sorry. If this was actually moving in a negative direction, then we would have to change the axes on this so that this was negative, it was minus at the top and positive down at the bottom.
How would you know if are we assuming the time axis is 0?
What do you mean? That this is 0?
This is 0 in position.
Yeah, unless you hear otherwise, that's 0. This end is
Okay,
positive,
okay.
and
So
this is
we
negative.
know for a fact that it is in the positive position.
We're assuming that. I'm not sure we can say for a fact because it wasn't expressly reported to us,
Okay.
but you could change it around. Sometimes students will do this wrong and realize it's wrong and then edit something up on the top. And as long as I've noticed that you've done that, like I just want to know that you can go between the two. So I'm going to say moves with increasing velocity. Just going to say that. Moves with increasing velocity. I don't know where it ends up. I don't know when it ends up. So I can't say it. You guys have any questions about number 2? Am I going too slow or too fast?
Good.
This is okay? All right. Ugh, all my numbers. I thought I had fixed those. All right, next one. If I put my slope-o-meter on my graph, I start with a positive slope and then it approaches 0. If I have a flat line up here, that's where my velocity is 0 meters per second. So I know when I look down here, if this is positive at this end and this is 0, I'm going to start with positive and I'm going to end up at 0. And I can just draw a line between them. Okay. The line on my velocity versus time graph is constant and negative. It's telling me that my velocity is getting smaller with time. It's approaching 0. If it goes past that, it'll become more negative. But at any rate, it's moving towards the negative side of the graph. So that's telling me that I have a negative acceleration. So negative slope, that's constant, tells me negative constant acceleration. So this should be a straight line across there. To graph this, I'm going to start at a position that's a little bit past 0. I'm going to move in the positive direction, but my dots are going to get closer to each other because as time goes on, the displacement is less. So I'm going to start kind of spread out and then move them closer together. I'm going to copy them for my acceleration motion map. These arrows I would expect to get shorter based on the pattern that I see in my velocity versus time graph, and they do. And then for my acceleration versus time graph, I've got a constant negative acceleration. So I'm going to have arrows that are constant in length, they're all the same, and in the negative direction. All right, next. Object starts at a positive position and moves in positive direction. I'm going to say with decreasing speed. So that's what's happening here, right? The speed is getting smaller. This is my least favorite representation of motion, by the way. I don't know if you guys noticed. Graphs are better.
Yeah.
All right, starting with number 4, we have one that's split into 2 pieces, and that's there to make our lives easier, and it might have helped with your notes too. So here we've got a constant slope that is 0. So with the slope of 0, we've got 0 meters per second for our velocity. This also has a slope of 0. That's telling us that our acceleration is 0 meters per second squared. So this goes down here. That was fast. What about this curvy one? Okay, so we know that it's starting at 0 at that point. So we know that there's going to be a velocity of 0. And then what happens as time goes on, this line becomes more and more, the slope becomes more and more negative, which means the change in the negative direction is greater with each second. So when I look at my velocity versus time graph, we're going to extend that downward. Now my velocity is decreasing or increasing in the negative direction. So I've got a constant slope here, and it's negative. So when I draw my acceleration graph, it's going to be a constant, straight, flat, horizontal line in the negative space on the graph. How'd you guys do?
Meh.
Meh? Fair. All right, so our motion map. We have an object that sits still for a few seconds, right? Sits still, doesn't move, sits still, doesn't move, starts to move. So when I draw my motion map, I'm going to have several dots that are in the same place. Bloop, 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 bloop. And then it's going to move away. And as it does that, they're going to get farther apart. The difference vertically here changes more dramatically as time goes on. So I'm going to stay pretty close. And then move away. And then move away. Move away. You see it? Now, this is one of the ones where sometimes I see more errors between the two. Remember, the location of the dot is only an indication of position. And so it doesn't matter which graph you're looking at, the position should be the same. So I'm going to just copy my dots. My velocity versus time graph should be a horizontal line that's between the 2 dots. So here I'm going to have a short one, longer, longer. Any questions about that one? Feel okay about it? All right. For our acceleration, we've got 0 acceleration at the beginning, so these vertical dots don't get any arrows. No acceleration. After that, we have arrows that should go in the negative direction. So the arrows go in the direction of motion, and they all should be the same, because if we tucked them under here, these would all be the same length. And again, just like before, if we took the length of our velocity arrow plus the length of our acceleration arrow, we would get the length of the new velocity arrow, which is pretty cool. For a description, I'm going to say my object sits still for a few seconds. Then moves in the negative direction. I always want to say something about direction, and I always want to say something about speed or velocity. And here I'm going to say the velocity is, you could either say increasing in the negative direction or the velocity is becoming more negative. I know it feels really awkward to say velocity is decreasing, but that would be true too. Jacob.
For my description for like the first part, I put the object is motionless for half the time.
That's fine.
On the ground.
Yeah, that's fine. Yep. Like there, we're just looking for the idea. I'm not trying to get you guys to match the words that I would use. I just want you to be able to describe what's happening with the motion. One thing that students kind of will sometimes mess up a little bit is they'll describe the graph. So instead of saying that the object was still, they'll say the position versus time line was horizontal. Something like that. And you're describing the graph if you do that. So that's the biggest thing that I see students do. So I'm gonna say it moves in the negative direction. I'm gonna say with increasing speed because that's what feels comfortable to me. Right? I can talk about speed as long as I give a direction. That's okay. Any questions about number 4? Okay. So I just want to keep an eye on time. I might go a little faster. Is that okay? Okay. So we've got some more that are lines that are split up into 2 parts. The straight part, I'm actually going to kind of skip here a little bit. So do you guys see this line here? Looks a lot like this line here. It's just the axes are in a different place. So when I'm looking at the second part of number 5, my line, what's with my numbers? I've got a constant positive slope, which means that I have a constant positive velocity. If my velocity is constant, it means I have 0 acceleration. And because this relationship looks like this one, I can just copy this. Positive velocity, 0 acceleration. We can learn to be time efficient, right? All right, next part. If we look at this first part here, we know that we've got to end up at that point, and we know that at the beginning it's horizontal, so there we're going to have a velocity of 0 meters per second. So we're going to start here, end up there. The velocity versus time graph gives us a constant positive slope at the beginning. So that means we've got a constant positive acceleration at the beginning. All right, so we started at 0. We start out slowly, so they're going to be close together, and then spread out. And then at some point, our dot is going to travel at the same distance per second as it did before. I'm just going to copy these. Velocity should have arrows that kind of change length and then become constant. Acceleration is going to be 0 at the end. So after this little dash line that I drew to kind of go with the dash line that was up here, I'm not going to have any acceleration. Before that, I have a constant positive acceleration. I'm going to have arrows that are all the same length before that. So description, we start at 0. And then we have a positive acceleration, right? Or you can say speeds up, or you can say the velocity increases. And then we have a constant velocity. Any questions on number 5? How are you guys doing on these? Okay?
Mm-hmm.
Yeah, all right. All right, number 6, we just have to finish this part at the end. We know that we're going to start at the same velocity that we ended up at with the earlier portion of this. And then our velocity is going to approach 0. So by the time we're at the end here, we're at 0 meters per second. So there we go. So this is a constant negative slope. So that tells us we have a constant negative acceleration. So we'll make that. I think it's kind of interesting that these velocity and timelines look like mirror images of each other, but these two aren't mirror images and these two aren't mirror images. I just think that's kind of interesting. For our motion map, we're going to start with a constant we're going to start with a constant velocity here, which means the dots are going to be evenly distributed through that space. And then after that, they're going to, our displacement is going to decrease so that they become closer and closer together. So we'll have dots that are evenly distributed, and then they start to get closer together. So there's our velocity arrows. Our acceleration arrows at the beginning, we're going to have no acceleration, and so no arrow length. It's only at the end that we start to see arrows, and they're in the negative direction. All right, putting them here, they're going down. So these arrows are going to be, they're going to look backwards. They're going to be the opposite direction of the direction of motion. Keep in mind that what this means is that we're taking our velocity, and if we're going to add something that's going the other direction, it means that our next arrow is going to be shorter, right? So because our velocity is getting smaller. So our object starts at 0 meters. It moves in a positive direction with a constant velocity. Then it slows to a stop. Any questions about number 6? Almost there, guys. All right, the last two are broken up a little bit. This one's fun. Curvy ones are funner. Okay, so at the beginning we have an object that starts pretty far away from 0, and it's going to move in the negative direction. The slope on our position versus time graph is constant negative, so we have a constant negative velocity. If we have a constant velocity, we have 0 acceleration. Then our object is going to, at the beginning of this dashed line here, it's going to have the same velocity as it did at the end. And then that velocity is going to become increasingly negative. So it's going to be a bigger number, and it's going to become more negative. So when we look at our graph, we start where we ended up, we become more negative. That relationship tells us that we are getting faster in the negative direction, right? It's moving towards a bigger negative number. So we have a constant negative acceleration. Our motion map should look something like we start far away, move with a constant velocity towards 0, and then at some point we speed up. So the dots are going to be further apart from each other. I kind of drew mine too far. It didn't go that far in the picture. Copy them down here. For acceleration, I have no acceleration at the beginning. As long as each of these arrows is the same distance, I don't have to add anything to them. But then they're going to get longer towards the left, and so that correlates with having negative acceleration. Because if I'm going to add velocity in the negative direction to something that's already moving in the negative direction, it's going to become more and more negative. So object starts, I'm going to say in a positive position. Moving toward 0 meters with a constant velocity. Does it make it harder for you guys if I abbreviate things? Is that okay? Oh, sorry, that's hard to see. Object starts in a positive position, moving towards 0 meters with constant velocity. And then object accelerates in the negative direction. Anybody have questions about number 7? Okay. Number 8. Last one. Woo! Today's been funny because I feel tired, and I feel like most of my students have felt tired today too. You guys are like, yay. All right. So for number 8, I'm going to look for some things in here that can help me kind of anchor what I'm going to do with my velocity, because this is curvy and complicated looking. So what I notice is that at the beginning and at the end, I have horizontal parts. And so those are both parts where my velocity is going to be equal to 0 meters per second. And I can go ahead and put those points here on my velocity versus time graph. then I need to figure out what happens in between. If I take a look at my slope, it starts out at 0 and then increases. The slope becomes steeper and more positive, so it's a bigger positive velocity. So I have something that's going to go up. After that, I start at kind of that peak slope there and then approach 0. So my velocity versus time graph then is going to have a line that just comes straight back down. So I have a turnaround point there. Kind of looks like a turnaround point. That's not what it says here, though. It's just where it starts to come back. Then for acceleration, what I'm going to do is look at my slope and my velocity versus time graph. At the beginning, I have a constant positive velocity, so that tells me I have a constant positive acceleration. In the second half, I have a constant negative velocity, so constant negative acceleration. What does this mean for our motion map? This is actually, I think this is a fun motion map, to be honest. At the beginning, we're going to have a small amount of displacement, the most displacement in the middle, and the small amount at the end. So when we draw this guy, we're going to start pretty close together and then spread out and then come close together again. I'm just going to copy these for the acceleration map. And then draw my arrows. So they start out small, get bigger, and then get small again, which is exactly what happens with our velocity versus time graph. We start out with small arrows, and the arrows get longer and then shorter, but they're always positive. They're always in the positive direction. At the bottom, we start with a positive acceleration and then end up with a negative one. So at the beginning, where our arrows are getting longer, we're going to have arrows that are in the direction of motion that are all about the same, and then they turn and go the other direction. So at the beginning, there's a force pushing it forward. At the end, there's a force pulling back on it. You guys are all packing up. Okay. I've already said kind of what the script is here, and I'm going to take a couple of minutes to talk about something else. I asked for a personal day tomorrow, so that hopefully I can see my dad like during the day. So what'll probably happen whether or not I'm here, is that you guys will be working on worksheet number 4. And so worksheet number 4 is a lot of graphs that have to deal with acceleration. So now that you've looked at some things qualitatively, just the way that relationships ought to look, you're going to try to calculate some things. So don't pack up too much. I want to give you guys some tips. You ready? Yes. All right. So at the beginning, it'll ask you between what points is the object speeding up. All the points have names, and the names are letters. Okay. You should know that. On the second page, you're given some data that's already on a graph. Yay. And then there's some things here to calculate. So in case you don't have these someplace else, displacement is your final position minus your initial position. Your average velocity is going to be your displacement divided by your change in time. So this steps you through something. Do pay attention to what these times are. Most of them are 2 and 8, but down at the bottom it asks about 5 seconds. Instantaneous velocity, remember, your instantaneous velocity is the same as your average velocity of 2 points that are equal distant. If you kind of get stuck here, go look at the first worksheet, because there was a problem there at the beginning. You guys remember the first worksheet? Yeah. Back in the day? Where we figured out the instantaneous velocity at 3 seconds by looking at the data at 2 and 4, or 1 and 5, or 0 and 6. So you can do the same thing with these problems. If you need to know the instantaneous velocity at 2, then use the data at 1 second and 3 seconds, or 0 seconds and 4 seconds. You should get the same answer no matter which ones you look at. Average acceleration is related to this. So your average acceleration is going to be your change in velocity divided by your change in time. Now keep in mind, if you need to know your average acceleration from 2 to 8 seconds, you need to know your instantaneous velocity at 2 seconds and at 8 seconds. So part E here is setting you up for part F. And then the instantaneous velocity at 5 seconds, that again, guys, is going to be average velocity of either 4 and 6, or 3 and 7, or 2 and 8. So you can figure that one out too. On the back, there's just some more things here. Remember velocity versus time graphs? And if you look at the area under this, it tells you about displacement.